All right, so our difference in the decibels and our sound intensity levels is 30. And so I1 over I2 is equal to 10 delta L over 10. And then you would solve that for the ratios, because I'm looking for this value. What is the number of times as intense that the 50 dB sound is to the 20 dB sound? So what is the ratio of their intensities, basically, is what I'm asking. And so that would be 10 to the delta L, which is 30, divided by 10, or 10 to the third. And so if something has a 20 decibel difference, then it's going to be 100 times more intense. If something just has a 10 decibel difference, it's going to be 10 times more intense. Not 10 plus, but 10 times, a factor of 10. Okay? So you'll probably see a question like this where it's just, an order of 10. 20 to 50, 30 to 40, some difference in decibels that's an even value of 10, 10, 20, 30, 40. And in that case, you really just take the first number here, divide this by 10, and that gives you the exponent for the ratio difference. So if it was, say, 10 to 50, what would be the ratio of the intensities? 10 to 50 dB, what would be the ratio of the intensities? 10 to the fourth, right, or 10,000, right? 1, 0, 0, 0, 0, 0.
So it's always going to be something that is 0.
Yeah. Yeah, I'll give it to you that way. Now, you might also see some questions. You will see a question, actually. Where is it? Well, I think one of that OpenStax question was a dB question. You want to look at that? Was it? All right, so an intensity level question. All right, so sound intensity, our sound level in decibels is 97 dB, and S2 is 91 dB. Calculate the ratio of the intensities. So here, this one's a little bit different. You could see one like this as well. Or it's the same, it's just how you work it is a little, no, it's still the same. So I'm looking for the ratio of these intensities, I1 to I2. Let's see, is that right? Yeah, I1, because that's the louder of the two. It'll go up top. And then this is going to be equal to 10 to the delta L divided by 10. And I'm looking for that ratio. So that's going to be 10. The delta L is 97 minus 91. So that's going to be 6 divided by 10. So it's going to be 10 to the 0.6 power. On your calculator, you have to use the Y to the X button. So you do 10, or just use your caret, 10 to the 0.6 power. And I get 3.98, so that's equal to 4. So 4 would be the right answer for that one. Okay? Have any other questions about OpenStax? I'm not going to sit here and work through all of them, but if you have questions about them, I'll certainly. No? What are some particular topics that y'all want to look at? Or particular questions that you have about exams? On OpenStax? Yeah. You okay if I show you your answer? Yeah. Okay, number 17. Okay. Just what? Well, what are you just putting random numbers up in here? Okay, so here this is, what is the difference in the sound intensity levels? So here, instead of solving for I1 over I2, you're solving for delta L. So it's the same problem, I1 over I2. We know what that is. That's equal to 5. That's the ratio of the intensities. And that's equal to 10 to the delta L over 10. So here we're solving for delta L. Y'all know how to solve for delta L? What do we do to get to that delta L? The what now? The log? Yeah, you take the logarithm. Right, you take the log of both sides. It gets rid of it here, and so you get the log of 5 is equal to delta L over 10. And so the log of 5, not the natural log, but the log, is 0.69897. You multiply that times 10, 6.9897. Okay? No, Natural log only comes into play when you have the exponential, the e to the x. Right, it's logarithms have a base, and the log that we use is a base 10, because that's our number system. but natural logs have a base e instead. So they operate the same way mathematically, they just have a different base. Okay? All right. What else, people? They are brimming with questions. I wasn't planning to go over all the various topics like we did in class. I think everybody was there except for one of you. That's okay.
This might seem dumb, but erect means upright.
Right. Mm-hmm. Yeah, you will see a lot of OpenStax questions, so please review those. Let's just sort of thumb through this exam that I have pulled up here. Again, you're not going to see any human body things, but you're going to see diffraction gratings, and you're going to see interference patterns, and you'll see these intensity levels, like this number 19. You'll see two-end systems. You'll see ray diagrams like this, aberrations and phenomena, the different kinds of images that are created by lenses or mirrors.
That number 7 right there,
Mm-hmm.
that was an OpenStax question too, except the choices were total constructive, total destructive, or a little bit of both.
Yeah, that's the same as C. That is neither total constructive nor total destructive. Which would it be in this case? I have two waves of wavelength 4 meters. The first travels 8 meters, and the second wave travels 12 meters. So what is the path length difference here? Is it 1? No, one travels 12 and one travels 8. So what's the difference? 4, right? And so how many wavelengths is that? It's one wavelength, right? So is this constructive, destructive, or something else? Constructive, because look, my path length difference, the PD, is equal to 12 minus 8, and that's equal to 4. You're going to see one like this. I just want to make that clear. So my path length difference is 4 meters, and that divided by the wavelength, the path length difference divided by the wavelength is equal to, since the wavelength is equal to 4, that means that my path length difference is 1 wavelength. And since it's offset by 1 wavelength, that is constructive interference, right? That's when I have waves that look like this, and the second wave is offset by a full wavelength. So I get constructive interference.
How do you get 1 wavelength?
Oh, because the path length difference is 4, and the wavelength is 4. So the path length difference is equivalent to 1 wavelength. Right, if this was 8, it would be 2 wavelengths. If this was 10, it would be like, what, 2.5 wavelengths. In which case, if it were 2.5 wavelengths, it would be what? Destructive, right. And if it was something that was neither a whole number nor a something half, it would be some combination of destructive and constructive. Okay? Let's thumb through these. All these questions are good. I mean, if you're having trouble with any of these, we need to address it right now. Anything jump out at y'all? Yeah. Leah? Okay. Let's see. Where's a good one? So, what I'm going to do, I'm going to go to this page, the homework page. Y'all probably don't go to it very often. But on chapter 7, I have all the ray diagrams, and there are videos too, but let's just take a look. I'm going to download this. These are in your workbook too. at the end, there's all your ray diagrams, and then there are also figures online where you can work on these as well. Or there are videos, rather, where I go through them. But remember, as I told y'all, they're going to be the harder ones, right, that you'll have. So let's just not do the easy ones. I'll just skip over those. I don't know that they're harder. They're a little bit more complicated. So here, if I have a concave mirror with the object inside of the focal point, I go parallel to the axis like that, and then I go through the focal point. So it looks like that. That was rule number 1. Second, I go through the focal point, then parallel to the axis. But remember, it sort of does this funky thing where I have a ray that goes up like that, and it's like it's originating from the focal point. So that's what it means to be from the focal point. Because, since it's in front of the focal point, my ray can't go through the focal point. But I draw it in that way. That's sort of like it going through the focal point. And then it goes parallel to the axis. And then the third ray is to go through the center of curvature and then back on itself. But again, I do this funky thing where I draw a ray that looks like it comes from the center of curvature like that, and then it reflects back on itself. And then to find out where the image is, I trace all 3 of these back. And where that is where my object's going to be, or my image rather. So my image is up here. It is a virtual image. It's upright and it's bigger. That's like our big makeup mirror. That is a makeup mirror. It makes you bigger, it makes you upright, and it's a virtual image. Also, you can do a 4th ray for mirrors. I go to the center of the mirror, and then I follow the law of reflection. And notice it goes back there as well. For the second one, this one's parallel to the axis is the first ray. Let's do it in the same color as we did before. Parallel to the axis and then through the focal point. But look, this is a diverging device. That means that the rays diverge from one another. And so that ray is going to go in this direction. Notice how I drew that I have a ray, but if I were to trace it back, it would go through the focal point. So that's what this means. Parallel to the axis, through the focal point. Even though the ray is not actually going through the focal point, it's actually the virtual ray that's going through the focal point. The second one is through the focal point and then parallel to the axis. This one goes, you have the ray go up such that if you were to trace it forward, it would go to the focal point. And then it goes parallel to the axis. And then the third ray, you can do to the center of curvature. Have a ray that goes up like that, such that if you were to trace it back, it would go through the center of curvature. And then it reflects back on itself, and it goes back in that direction. So if I trace my virtual rays back, I have a virtual ray right here. I have a virtual ray right here. I'm just tracing those reflected rays back. And then I have a virtual ray right here. So my image is going to be right there. That's a convex mirror. Knowing your images will really help because you'll know for the situation sort of roughly where the image is supposed to be. And if you have virtual rays drawn, which you will, right, because it's those more difficult ray diagrams, then you'll know where to look to find the image. Like here, you know that the image needs to be smaller and needs to be on this side of the mirror. So you can look and see, is there a spot where all the rays meet? And you should have 2 or more rays meet there on the question, right? Because you're looking for either the correct or the incorrect rays. So more than one will be correct or more than one will be incorrect. And if there's a spot where 2 or more rays connect, and it meets the criteria for what that image should look like, then it's probably the right answer. All right, those are probably the correct rays, and you should be able to pick out the incorrect ray. Does that make sense to you? What I just said? We'll look at an example here in just a minute. Let me show you the lenses. They're similar. Listen, there are videos online if you want to look at those too. Or if you're not clear, you can stay after and I can go over it more in depth. Let's skip those two and go to the more difficult ones. These are parallel to the axis and then through the focal point, like that. Through the focal point and parallel to the axis. How does this one go? It goes like this. Through the focal point, like this, and then parallel to the axis. Yeah, that's right. And then the other, for rays, or for lenses, it's a lot easier because there are just 3 rays. I just go through the center of the lens. And then if I want to know where this meets up, I trace back all the rays, the refracted rays. These are my virtual rays. And then this is where my image is. But I know that for a convex lens, when I'm inside the focal point, I have to have a virtual, upright, bigger image. It's like a magnifying glass when I'm inside the focal point. So that makes sense with what I already know, that I need a virtual, upright, bigger image. So it usually should help that to sort of guide your ideas. Okay, this one, parallel to the axis. This was the trickiest of all of them. And then through the focal point, but this is diverging, so that ray goes up such that if I were to trace it back, it would go through the focal point. And then through the focal point and parallel to the axis, this is the trickiest of all, because you're not going through the focal point on the left-hand side, you're going through the focal point on the right-hand side. Let me see if I can get that. So I have a ray that goes forward such that if I continued it on, it would go through that focal point, and then it goes parallel to the axis. And so if I trace this ray back, it's going to meet up with the blue ray right there. So I already know right now that my image is going to be right there. A smaller, upright, virtual image. Just like for convex mirrors, the security mirrors, is what you expect. And then we can just have one that goes straight through the center of curvature. These are hard to draw on a computer, but you won't have to draw them, fortunately. Goes through the center of curvature on that side. And then it traces back, and it crosses up with all of those. Let's look at an example question so you get an idea of what it'll look like. Well, like for example, this one right here. Which one of these is wrong? Well, I just take them one by one. Parallel to the axis, through the focal point. That one seems okay, right? It is. Through the focal point, parallel to the axis. This one, I don't know, this one just goes to the edge of the lens and then parallel to the axis. So this B is not correct. So B is the one that's drawn incorrectly. All right, you might have more than one that's drawn incorrectly, or you might not have any at all drawn incorrectly. So make sure you go through and look at each one carefully, and make sure that it follows one of those rules. I can tell this is wrong, that one of them is wrong, because I have places where 2 rays meet up. Right here, I have rays meet up, and right here, I have rays meet up. Now, I can't tell which one is incorrect, because both of those create real inverted images. And I know that's the kind of image I'm supposed to have, so I can't discern between either one. Okay? I guess that you could discern that either it has to be A or B have to be incorrect, because C is coincident with both A and B. Y'all follow what I'm saying? Let's look at another one. That was spring 17, am I right? Let's see if spring 15 had one. I'm sure they did. Oh yeah, look. So here's one. I have 3 rays. Are they all incorrect? Well, they should have no image formed. Right? You're right about that, that there should be no image Which ones are wrong? 2 is wrong. Right, 2 is wrong because this ray right here should go through the center of curvature. It should come here and then go back on itself and go in that direction. What about this ray? It goes parallel to the axis, and then where does it go? It should go to the focal point, but it's going to the center of curvature. So this one's wrong. What about 3? Is it wrong? No, 3 is okay. It's just following the law of reflection. So both of these are wrong. 1 and 2 are wrong. You're going to see a question sort of like that. All right? It's not going to be this exactly, but it'll be one of those 4 scenarios. It'll help you to know your images, what type of image to form. I know I've said that several times. But if that is true, it will help you on the test on more than just ray diagrams. All right? Again, look at those videos. I go through those ray diagrams if you're having difficulty with them. Or come see me, I'll help you. It's hard to do it here correctly without a ruler. What else? People? No. She's asking about, do you have to know nodes or resonances or anything with tubes or sounds in tubes, open-ended tubes, closed-ended tubes? We didn't do any of that. We skipped over that section in chapter 9. So no. Is that all you got? More questions? I'm here for you. Okay. Oh, yeah, let's talk about that.
I just want to clear something up on...
You need to clear the air? All right, go ahead.
No, spring 16 number.
Oh, on the test. Okay. Spring of 16. Exam 4, spring 16. All right, which one? Number 11. Okay, so here I want to know what is the path length difference. At this point, I know that it has to be an integer number or a half number of wavelengths. It's a dark spot right there. So what do I need? I need a half number of wavelengths. So already I can get rid of A and C. So with this, I have here at the center point a 0 wavelength path length difference. The 2 waves have had a 0 path length difference. Here at this dark fringe, I have a half a wavelength difference. This is 1 wavelength, 1.5, 2 wavelengths, 2.5 wavelengths. So the dark spots increase by half wavelengths. So if I have an interference pattern that looks like this path length difference is 1 wavelength, or excuse me, 0 wavelengths, a half wavelength, 1 wavelength, 1.5 wavelengths, 2 wavelengths, and on and on. And that's true whether you're looking at single slit, double slit, or diffraction gratings. It doesn't matter. It's still an interference pattern. And it's just comparing your path length difference, the difference that the 2 waves have traveled, to the wavelength of the light. Okay?
And it says isn't it bright fringe and the arrows pointing at the dark ones?
Oh yeah, that's just a typo. It should say dark fringe. Yeah, that is a dark fringe. Okay? Sorry about that. That was really your question.
Yeah, I was confused because it was bright and the question is one paper.
Yeah, sometimes I do that. Like, sometimes I sit around my office and say, what kind of mistake can I make to confuse the students? Because I don't want them to do well. What else? Yeah, which ray is drawn incorrectly? Well, let's see. A goes parallel to the focal point, through the focal point, parallel, to the edge of the lens parallel. Which one's incorrect? C is incorrect. Yeah, I don't know where this ray C would go. It would not go that way. It would go somewhere else. It would go not quite parallel. Like it's not one that we've done. It would just sort of go off in this direction, probably slightly, maybe like in that direction. Okay. Yeah, idea. Yeah, of course. It would be right here. It would be upside down. It would be real, and upside down and real. It could be bigger or smaller. It could be the same size too. Yeah, it depends where the object is with relation to the focal point. That's all. 17?
Yeah, 27.
Okay, so good question. If I increase the tension in the string by a factor of 2, what happens to the frequency? Frequency is 1 over 2L square root of T over mu. So if I'm increasing my tension by a factor of 2, first of all, tension is T. And so that means I'm increasing this by a factor of 2. So what is my new frequency? If I increase this by a factor of 2, I have a root 2 factor over here. Y'all follow why that is? Because I'm increasing this 2 here, but it's under the square root sign. So if I increase this by 2, I get a root 2 over here. If I increase this by 2, I get a 1 over root 2 over here. 1 over the square root of 2. And so root 2 is about 1.4. So it's going to be about 1.4 times 320. E, I guess. Yeah.
And you said that if it's 2 mu, then it would be square root of 1.
Right, yeah, so if I asked, what if I increase this by 2, then I would have a 1 over root 2 factor. If I increased this by 2, I would have a 1 over 2 factor on the other side. Or if I decreased this by 2, if I had this as a half, I would have a factor of 2 over here. Let me write that again. It's a good question. I mean, you will see one similar to this. 1 over 2L square root of T over mu. Like, what if I said that I decrease L by a factor of 4? That means I would increase the frequency by a factor of 4. Just want you to look at, are they inversely or directly proportional, and how are they related? Is it a linear relationship or this square root relationship?
So if it would be like half T, you do the square root of a half.
That's right. Yeah, so if I had a half, whatever I do on that side, I have to do on this side. If this was a half, it would be 1 over the square root of a half. Y'all follow me? It's a question on the test, so if you're not, please. Yeah.
Can we look at 21 from spring 16?
Mm-hmm. Okay, so this goes back to our intensity is equal to our power divided by area. So I want my intensity to drop by a factor of, what, 100? Because I'm doing 0.1 divided by 0.001. I'm going from this value to that value and that's going to be 100, right? Yeah. I want my intensity to drop by a factor of 100. And so in order to do that, what do I do to my area in order to make that happen? Well, I want my area to also drop by a factor of 100. And so you might think D is the right answer, right? But it's not, right? What is the right answer? That's the question. It's 10, right? Why is it 10? Because 10 is the radius, and area is 4 pi r squared. So if I want to increase my area, by a factor of 100, I increase my radius by a factor of 10, because it's squared. And that's what I'm doing. I'm going from 1 meter to 10 meters. So I've increased my radius by a factor of 10. Let's write that out again. So intensity is power over 4 pi r squared. If I increase this by 10, I decrease that by 100, which is what I want to do. Decrease it by 100. If I move 10 times as far away, my intensity drops by 100 because it's squared. Okay? Question. What else, yeah?
So you did the 0.1 over 0.01 to get on.
Yeah, because I'm going from 0.1 watts per square meter to 0.001. In order to get that, I have to multiply this times 1 over 100. So, you know, I would get that 1 over 100 by saying 0.1 over 0.001. Right. But the question is, you know, what is the factor difference between this intensity and this intensity? All right. Is that all? Good, I guess. I'll be in a Yeah. All right, I'm going to stop this.